Welcome. This is Small Head, Big Problems. I'm a small head and I've got big problems. Today we are solving three TMUA problems with no preparation in hopefully less than 10 minutes. I have miserably failed at that pretty consistently over the past episodes, but I'm gonna keep trying. I'm not gonna give up. 10 minutes. Come on. I'm gonna continue making my way through the 2016 paper, starting with problem 13, if I'm not mistaken. Hopefully, I'm showcasing the kind of thing you need to do well in your TMUA, which is being resourceful with potentially quite unfamiliar problems under significant time pressure. And, you know, hopefully you're having fun watching me fumble around making stupid mistakes. We're all human. Um, yeah, do try the problem yourselves before you watch my solutions. Two solutions may look quite different, but remember that the TMUA is a multiple choice exam that does not require showing any workings, so the point is just to get the correct answer as fast as possible. You don't even need like a really great justification, right? As long as you have the correct answer, I'm happy. But yeah, I mean, if you want to explain to people how you got there, then you better have a good explanation to put in the comment section. All right, let's go. How many real roots does the equation 3x to the 5 minus 10x cubed minus 120x plus 30 equals 0 have? Okay. Wow. So this is definitely a little different, something I wouldn't necessarily expect to see on an A-level paper, because it's a quintic equation. You can't just use like the discriminant or anything, right? Like the discriminant is for quadratics. Um, so yeah, you need to do a trick that I don't think they really teach in A level, and I've recently kind of come across it in the TMUA for determining the number of real roots to some polynomial equation. I was doing it with a cubic, right? And but it will work for this quintic, I hope. Um, and what you do is you find the turning points of this function, right? And you find out where they are, right? Because this is a quintic, so it sort of starts at minus infinity, ends at plus, and it may have like up to four turning points, right? So like say like has a turning point here and here and here and here and boom, right? One, two, three, four, right? So depending on basically if there is a sign change between these turning points or not, right? Like what the sign of the function is at these turning points, um, then you'll be able to tell how many solutions there are. So for example, here there are three solutions because we've come down from minus infinity and my first turning point is negative. So we haven't, um, we haven't passed the x-axis so far, right? Then I have another turning point here and okay, whatever. And haven't passed it so far. Then my next turning point is positive, so that means I've passed it. And my next turning point is negative, so that means yeah, like there's been a sign change, and we've crossed the x-axis in between. And then I go up to plus infinity, so that means I'm going to cross the axis one more time, right? So that's the idea. We're going to find the turning points, and yeah, like the turning points should basically tell us basically we should get like a good sketch for the function is the idea. Okay, cool. So we'll differentiate it. There you go. And set it equal to 0. So that's the beautiful thing about this quintic. Like if it was some kind of random quintic, it would be really hard to find the turning points because you'd be, solving like a quartic equation. But this is a hidden quadratic, right? Quadratic in x squared. So I'll go ahead and divide by 15, get those big numbers out of the way. 8. All right. And hopefully I can factorize this one. Let's see. 8 is 4 and 2. Yeah. Well, 4 minus 2 is 2. Okay, so I can do this. So x minus 4, x plus 2. Well, x squared, sorry. All right. That work? That works. Okay. Um, so either this is 0 or that is 0. For the second one, immediately, you can see that, yeah, that's not going to give us any solutions because we get x squared equals minus 2. And yeah, that doesn't have any real solution. So nothing coming from there. And then here, x squared equals 4. So x equals plus or minus 2. All right, so we have two turning points. And then we just need to, evaluate the function at these turning points. All right, this is going to be a bit long. But y at 2 and y at minus 2, what do we have? So y at 2, 3 times 2 to the 5 minus 10 times 2 cubed, etc. Let's see. Gotta know your powers of 2, right? Gotta love your powers of 2. Right. I mean, I can see pretty clearly that's gonna be negative. That's gonna be negative. I don't care exactly what. It is pretty clear to me from the numbers that that's the case. Um, from minus 2, let's see. Well, basically, it's if I put minus 2 in these odd powers, x5, x cubed, x, I'm just going to get minus the answer I would have got if I plugged in 2, right? So it'll be like minus 3 times 32, which, by the way, is 96, okay? Minus 96 plus 80 plus 240 plus 30. That one doesn't change, the constant term. But yeah, that's clearly positive. Okay. All right. So basically, yeah, well, this is our graph. It comes from negative infinity. Minus 2 is a positive turning point. So okay, we're gonna have like a root there. Then at 2 we have a negative turning point. So yeah, we're gonna have one here, and then it's just gonna go up like that. So three real roots, hopefully. Let's have a look at the answers. Yeah, so I checked the answers, and that is answer C. Awesome. Happy with that. Great. Go to the next one. The terms of an infinite series S are formed by adding together the corresponding terms in two infinite geometric series, T and U. Okay. So S is the sum of T and U. Okay. The first term of T and the first term of U are each 4. Okay. In order, the first three terms of the combined series S are 8, 3, and 5 over 4. What is the sum to infinity of S? Okay. Well, first of all, I mean, all you know in A level about sum to infinity, anything that converges would be like for geometric series, right? Which T and U are, right? And S is the sum of them. So of course, it seems logical that the sum of S to infinity is equal to the sum of T to infinity plus the sum of U to infinity, i.e. we'll find T and U separately and we will, um, you know, sum up the answers. We already know the first terms, right? So remember, like a geometric series, UN, right, would look like a first term A times R to the n minus 1, right? Where n goes greater or equal to 1, right? Where R is the common ratio. Yeah? So it's like A times R squared, etc. That's what a geometric series is. So starting with something and then multiplying by the same number R each term. And then the sum to infinity of something like that, as long as R has size less than 1, is A over 1 minus R. Okay, so that's as long as R is small, which is strictly between -1 and 1. Okay. So that's that. Um, all right, and so we have that the first terms are 4 for each, so that's good. We know what A is. So U is, 4R 4R squared. T would be 4, and then 4 times something else like S or S squared, etc. And we're told that the sum is 8. Well, that's not surprising, right? So S is the sum, is 8. That's not surprising. 3, right? And 5 over 4. So what does it mean? It means 4R plus 4S is 3. 4R squared plus 4S squared is 5 over 4. Okay. All right, so this is just like a nice little system. Let's see. I'm going to multiply that up by 4. And then notice, okay, so that's like 4R all squared, right? So I'll use this first equation. I'll just solve for 4R, kind of doing a substitution, but like kind of a weird substitution where I'm saving a bit on tedious arithmetic. There we go. I'm sorry, that should be an S. 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 Okay. Cool. All right, so we'll just, yeah, expand that out and solve it. It's a quadratic. So 9 minus 24s plus 16s squared plus 16s squared equals 5. Take that to the other side. So we got 4 minus 24s plus 32s squared equals 0. Can divide that by 4. Swap around the terms a bit. So 8s squared minus 6x plus 1. Okay. And let's see, can we factorize that? Well, 4 and 2, yeah. Yeah, so like 4s minus 1 and s minus 1, right? Sorry, 2s minus 1. Because 8 times 4 is, sorry, 4 times 2 is 8, and 4 plus 2 is 6, essentially. So we get s is a quarter, or s is a half. That's interesting. Two different options. I wonder if at the end of the day, that's just going to swap around the series s and t, right? So if we plug it into the equation for r, so 4r equals 3 minus 4s, so s. So if we take s to be a quarter, that means 4r is 2, so r is a half, right? But if we take s to be a half, then that means basically we'll get r to be a quarter. So essentially, like both the solutions are kind of the same solution, right? It's just like swapping around S and R. Um, so one of them is half, the other one is quarter. They both have the same starting term, so it doesn't really matter. Okay? So t to infinity, that's going to be, 4 over 1 minus, just take it to be a quarter then. Multiply that by 4 top and bottom, so that's 16. Well, okay. Don't want to go too fast. 4 over 3 quarters, right? So 4 times 4 over 3, so 16 over 3 for t. For u, take it to be a half, so 4 over 1 minus half is a sum to infinity. So 4 over a half, so 8. All right? And I just, for s infinity, I'll just sum them up. So 16 over 3 plus 8. So 16 plus 24 over 3. Let's see. 40 over 3. That's answer D. Okay, that's one of the answers. Hopefully is the right one. I'll just check. Yes. I checked and it is indeed D. Okay, cool. Cool. Doing well so far. Doing well so far. All right, question 15. The least possible value of the gradient of the curve y equals 2x plus a times x minus 2a squared at the point where x equals 1 as a varies is... Okay, so we've got a curve which depends on some parameter a, let's say, right? Some cubic. And we want the least possible value of the gradient at x equals 1, right? So the least possible value of f prime of 1, like as a varies. All right, well, fine. It's probably going to be like a quadratic, so complete the square. This is probably going to be a little bit easier. Um, so I'm just gonna like expand that out to differentiate it. That's gonna be easier. So first square that out. Expand that out. So for the x cubed, here we have it. Oh, wait, I need an x here. Um, for the x squared, I'll have a 2x times minus 4ax. It's going to give us minus 8a x squared and plus an a squared. So minus 8 plus 1 is minus 7a x squared. Okay, for the x's, I'm going to have 2x times 4a squared and a times that. So it's going to give us 8a squared minus 4a squared. So just plus 4a squared times x. And for the constant term, just these. A times 4a squared. All right. Cool. So differentiate this function. 6x squared minus 14ax plus 4a squared plus nothing. Yeah, I didn't really care about the constant term after all. And f prime 1, just plug in 1, so 6 minus 14a plus 4a squared. And as I expected, we get like a quadratic in a squared, right? So we want to find the minimum value of that. Yeah, so I mean, basically with quadratics, right, the minimum occurs at minus b over 2a. Well, you could just differentiate this expression again. So that's going to be minus b, so plus 14 over 2a, so that's 8. So yeah, 7 over 4. Okay. And then, yeah, just plug that in, right? We want that least possible value. So this is where it occurs. This is kind of the a, the minimizing a. And I'm just going to plug that in here. 6 minus 14. Let's see, bit of cancellation here. There's a 2 times 7. Wait, yeah, so 49 over 2, and then here 4 is going to cancel with this 4, so I have plus 49 over 4. Cool. So overall, 6 minus 49 over 4, which is 6 times 4, plug in 24 minus 49. I think minus 25 over 4. It is one of the answers. Let's hope that's right. The answer is C indeed. Yeah, nice. Of course you could differentiate this with the product rule. I wonder what would happen actually. Is there any advantage to that? It would it would keep it factorized actually. Wait, so let me, as a little bonus, stop the clock. Probably I failed still, but um as a little bonus, let's just differentiate that kind of using the product rule. So we got 2 times 1. Okay. So using the product rule and then the chain rule on that one. And yeah, like it's nice actually because mm, like you kind of get a factorization out of it, and that you know, I mean, there's that. Yeah, I mean, it's sort of nice. Like we get like a factor of 2 times x minus 2a. So get x minus 2a here. We could plug in 1 as well, but that's fine. X minus 2a. And then here we'll just get 2x plus a. So 2 times x minus 2a times 3x minus a, right? Plug in 1, we get that. Um, which, yeah, I mean, we don't really want we don't really, I mean, factorizing is kind of good when you want the roots, but you can also find the minimum, right? Because the minimum occurs like right in between the roots for a quadratic, right? Right in the middle. So for the roots, you'll get like a equals a half and a equals 3. And so, the minimum occurs right in between those roots. So if you just take the average of them, so you get 7 over 2, which is 7 over 4. So it's the same as we had before. Um, yeah. And then, still plug it in. The nice thing about like the factorization as well is you see kind of like that at the maximum always occur when like these two things are equal, actually. Which, by the way, is like, mm, yeah, yeah. I mean, also like a really cool way of kind of doing that, just setting these to be equal, right? Like one. So anyway, I'll show you. I'll show you like I'll show you like how that works. So 2 times 1 minus 2 times 7 over 4, and then 3 minus 7 over 4. And then you should get, let's see, what's that? 1 minus 7 over 2. Um, so that's minus 5 over 2. And here we get 12. Sorry, minus 5 over 2. Right. And here we get minus 5 over 4. Ah, okay. So not, I mean, sort of kind of same. It's just like I do need to um lend uh lend that for. Wait, sorry, no, wait, something doesn't make sense. What am I doing? Yeah, sorry, so that's plus 5 over 4 plus 5 over 4 here. Um, so yeah, if I just lend that 2 to this guy, you do get 5 over 2 times 5 over 2 pretty much. Yeah, so it doesn't quite work if there's like a coefficient there. Oh well. Um, yeah, but still, it's kind of interesting. Maybe there's something to it. Yeah. Well, there you go. Thank you so much for listening. If you enjoyed, please make sure to like and subscribe. And if you're interested in getting private tutoring, do send me a message. My details are in the description. See you next time.